pleased to welcome our first keynote speaker, Doug Oard of the University of Maryland.
Would you like the mic?
Okay, so we should get started. So I'm very pleased to introduce our first keynote speaker, Doug Oard of the University of Maryland. Doug needs to run to the airport right after this talk. So
Actually going to drive.
He's going to drive to the airport, not run. I don't want to go on too long, but I do want to say I want to thank Doug because he's been one of the biggest supporters of this school. There was a session at the Cigar Conference in 2017 where we were talking about how we could broaden participation in information retrieval and in related fields. And Doug gave a talk at that event, and he brought up the idea of doing something like this, a summer school in Africa. And he helped us set it up. He was our program chair last year, helped recruit a great program last year, and it went really well last year. And we're very happy to have him back. So thank you, Doug.
Thanks, Ben. So, I really appreciate the invitation to talk here. I was not expecting to come back. Those who start things should get out of the way and let other people bring new ideas. But this idea of being able to come back and see the beginning of this second event is very satisfying for me. I want to talk today about what I think of as the limitations of our vision. Charlie talked this morning about the sorts of things that we're building, the capabilities that we have to do things we haven't been able to do before at a scale we haven't been able to do them before. And I'd like to put a counterpoint on that with the things that we're not building and that we could be, and that this venue could be really transformational in helping us to think about things like this. So I don't want to claim that I've got all the answers. I don't even want to claim that I have all the questions, but I do have some questions and maybe some answers. I want to start out by talking not to the students, but to the instructors. Part of what we're doing here is learning. All of us are learning, and we're learning from you about the environment in which you work. And I have tried to capture a couple of points just to be provocative. All the things that Charlie talked about rely on text. That's not to say we can't do things with speech, but that wasn't what Charlie was talking about. All that text relies on the ability to read and write, and so it's a reasonable question. Can everybody read and write? Because, you know, I mean, there are some people who are blind, there are some people who are not literate, so there are limitations to the use of text. 19 countries in the world have adult literacy rates below 50%. Now, you have to be very careful about these numbers. These are people of all ages. Younger people tend to be more literate than older people. So if you just wait, these numbers improve. These numbers are all counted in different years. They're all statistical estimates, but nonetheless, 19 countries have literacy rates below 50%, and we are at the epicenter of that group of countries. And so if we want to serve our populations, we'd best ask, can we serve people who are not literate in some meaningful way? And if we can, it's about 1 billion people. It would be worth thinking about, a little less than 1 billion. A second thing is that the web has content in a lot of languages. It's a little fuzzy to try to measure exactly how many languages. In fact, it's a little fuzzy to try to measure exactly what a language is. But people who count these things, looking at widely used web pages, find 39 languages that are fairly easy to identify. the smallest of which accounts for 0.5% of the content on the web. So surely there's more out there in the long tail. But there's just not that much content beyond 39 languages. None of those languages are indigenous to Africa. I mean, plenty of them are spoken in Africa. English is spoken widely in Africa. French is spoken widely in Africa. Portuguese to some extent. But in Arabic is, I think I'm glossing over because of the focus on sub-Saharan Africa. We make the assumption, if we're going to provide internet services, that people have internet access. Charlie showed us these lovely pictures of the data centers. You know where the very best place to put a data center is? Someplace where it's cold, right. Iceland is just a lovely place for a data center because the cooling costs are lower and Iceland is very well networked. And because Iceland is very well networked, almost everybody in Iceland has access to the internet. Not so in Somalia, right? If you'd like to serve the Somali population, the first thing you have to do is get internet service, and nothing we build is going to make much difference. It might create a little demand signal, but there are problems you have to solve before that. Now, if those were the extent of our problems, I'm going to talk about the first two of these, and I'm going to leave the third one to Hussein, who's talking tomorrow? Wednesday? Okay. But the problem is worse than that. Now, this is a hard picture to see. This is a photograph taken from space. It's not taken all at the same time because it's not nighttime everywhere, but this is what the world looks like when it's not cloudy and when it's dark in the optical range. And as you can see, this is essentially measuring streetlights. There are a lot of streetlights in North America, but not so many out in the West because that's a desert there. There are streetlights on the east coast of Australia and around Perth on the west coast of Australia, but not so many in the center because nobody lives in the center of Australia. There are two little dots here. One of them is a city called Alice Springs, and the other is a secret Air Force satellite tracking station, U.S. Air Force satellite tracking station, which is a little less secret than they might wish it to be, and perhaps they should turn off the lights when their satellites come over. You can see that India, which would have been dark many years ago, or darker, has been electrifying. This is essentially a measure of electricity availability, if you think about it. Has been electrifying at a pretty good clip. Europe, you can identify the continents really well. Iceland isn't so heavily populated. Greenland, nobody at all. Antarctica, nobody at all. So the places that have no lights have no people, right? That's what causes there to be no lights. With a single exception, and that's this area here below the Sahara, right? Excepting Johannesburg, and anybody know what this is? Cape Town, right? This is not like Africa, right? I mean, this is like Cape Town. And so you can see a place where 1 billion people live that has no lights, which means it has no electricity, which means that getting the internet service is not the first problem. Getting electricity is the first problem. And once you've gotten electricity, getting internet service is perhaps the second problem. And then we have something to do. So we can't solve all the problems here, but we can solve some of them. I'll point out that this is a list of the, I think it's 19 languages, maybe it's 29 languages. 19 languages, that 50 million or more people speak, first and second language speakers counted together. It's got 2 African languages on it, Hausa and Swahili. Swahili mostly spoken by second language speakers, Hausa mostly spoken by first language speakers, and if we went further down, we'd find a larger number of African languages. So the problem with the internet not having content in languages that are indigenous to Africa isn't that there aren't a lot of speakers, it's that there's not a lot of money. And the people who have been putting content on the internet have in mind the money that the people who might look at it would have. So if we're going to build solutions, we have to build solutions that are affordable and effective for these languages. And you might want, because there is quite a lot of content in English and in Chinese, you might want to allow people who speak languages other than English and Chinese to find out what the hell those people are talking about by supporting cross-language retrieval, where people aren't searching just within their language where there is going to be limited content. I'll move a little more quickly through this picture. You can see here the growth of the internet in North America in green, in Europe and Central Asia in yellow, and different regions stacked up, and this region at the top is sub-Saharan Africa. The internet penetration is about 20% back when these statistics were taken in 2016. And so the good thing, there is good news here, is it's the most rapidly growing population of internet users. The reason it's the most rapidly growing population of internet users is that 3/4 of all people in sub-Saharan Africa have access to a cell phone. But only 1/4 of the population of sub-Saharan Africa has access to a smartphone, right? So 2/3 of the access today is through so-called feature phones, where you might use SMS to interact. But patience here is a virtue, since the cost of smartphones is going down, the availability of used smartphones is going up, and so you can imagine that the internet penetration in Africa could easily double in a rather short period, and there is no other place on the planet where that could happen. The other thing Africa has going for it is demographics. I was working in Tanzania. Is it Tanzania or Tanzania? Tanzania. I was working with some people in Tanzania without ever having visited. I need to visit sometime and find out how people pronounce this. And one of the statistics that I came across was that the population is remarkably young. Now, these are statistics from back in 2000, in part because the lifespan is, on average, 41 years. Imagine that if you're from Europe or from North America. This is just really hard to get my head around. The education investment in Tanzania is quite large, and of course these young people will get older, and the middle-aged people won't. There just aren't that many of them, and so the very tip of the population will move up, and there'll be a few retired people, but not very many. And as societies get wealthier, they tend to have fewer children, so it's a reasonable demographic projection that this does not continue to look like the towers of Hanoi forever, and it looks a little like one of those plums we saw the other day, where it goes up sort of level. The other place where you'll see a picture that looks like the 2050 version of Tanzania is China, which you might know was the most rapidly growing country on Earth by a factor of something like 3 for about 40 years. And that's what this picture looks like. It looks like very rapid growth over an extended period of time, because the so-called dependency ratio, which is the number of people who are too young to work or too old to work, to the working age population, is quite low under these circumstances. And so this is potentially an area of enormous growth. And thus, looking to the future, I think, makes a lot of sense. Okay, I'm sure that many of you are being polite and not correcting me on some of these statistics. So please have a conversation about these things while you're here. Right? That's what I want to inspire. But the story that I want to tell is a story of research in an effort to do something motivated by these issues. And so I want to talk about cross-language text retrieval. This won't serve everybody, but it will, by crossing the language barrier, maybe be helpful. And then I want to talk about speech retrieval. It's not cross-language, it's within language, but it's within any language, not just the languages where there's money. And then I'll finish up at the end with a few words about cross-language speech retrieval, which is a much harder problem, but worth working on. I have to start, though, by telling you a story from when I was a kid. So I apologize to those of you who were here last year who heard this, and I'll apologize to the rest of you that the story is a tad off color. It's not off color in a risque way. It's off color in a probably best not told in Africa way. But when I was a kid, I really liked elephant jokes. I mean, it turns out in the 1960s, elephant jokes were really popular, and in the 1960s, I was a kid. And so I thought elephant jokes were just the greatest thing. And my very favorite elephant joke goes like this. A guy goes into a shop, and he wants to go elephant hunting, and so he wants to buy a gun. And he says, what kind of a gun should I use to shoot an elephant? This is the not quite politically correct part, right? And I didn't realize at the time it wasn't politically correct. And the owner of the shop says, well, you should use an elephant gun, which, if you know anything about guns, is actually good advice. So he says, well, what if I want to shoot a blue elephant? The owner of the shop pulls off a blue elephant gun and says, then you should use a blue elephant gun, of course. You can see why I thought this was humorous. The next question is, well, what if I want to shoot a pink elephant? And the answer, of course, is there's no such thing as a pink elephant gun. Right? You seeing why I see this is funny? What you do is you take the elephant and you hold its nose until it turns blue. And then you shoot it with a blue elephant gun, right? Now, little did I know that my entire career would be based on that one joke. But if you want to think about how do you do cross-language retrieval, you just take one of the languages and you hold its nose until it turns blue, and now it'll look like the other language, right? And then you shoot it with your blue elephant gun, which is what Charlie was telling us about. So Charlie's talk was actually about blue elephant guns, and I'm going to talk about holding his nose until it turns blue. Okay? Now, as it turns out, Wikipedia has an elephant joke page, which has a great scholarly analysis of elephant jokes, and has that joke on it, which quite shocked me when I went looking for it. Okay, but so you can go there and see that and other elephant jokes. So that raises the question, where should we hold its nose until it turns blue, right? And if you look at this, there are really only 3 places you can do it, right? So the query comes in, and we build some representation of the query. This is the picture that we're seeing in the morning. The documents come in, we build some representation of the documents, and then we have some function that compares them, right? So you could just make the query into the language of the documents. That's a simple problem of translation, right? Or you could make the documents into the language of the query before you index them. Or you could leave them in whatever language they're in and let the comparison function figure it out, which is probably the harder solution, right? And so it's fairly obvious what to do. People call the first one query translation, where you translate the query. People call the second one document translation. You actually don't need a research talk for this, right? What you do need a research talk for is how are you going to translate the darn things? And the obvious way to do it is to use Google Translate. Sorry to the Bing people in the room. But that raises the question, what's Google Translate doing? Because you're really doing whatever Google Translate is doing, and then the question is that the right thing? And so you can think of three basic ways of doing it. You can use lexicons, look it up in a dictionary sort of a thing. So we have lots of online dictionaries. You can use text collections, either collections that are actual translations or collections that are on similar topics. You can just use things that are written in similar ways. So some words are just written the same way in different languages. And you can sound it out and see if it sounds out the same way if you have a pronunciation model, right? So this is similarity. This is learning patterns of language use. And this is using human codified language use, right? Those are the three basic sources you can use. Now, I'm only going to talk about one of those, which is parallel text, because it works better than any of the others. The lexicons are quite limited. You can typically get you do about half as well in maybe 70% as well by a typical IR evaluation measure, like Charlie was telling us about NDCG, as you would if the query had been in the same language as the document, right? So you cross the language barrier with the dictionary, you get to 70%. With translations, you can get up near 100%, and cognates are much lower than that. So I'll just talk through this one way of doing it just to illustrate it. And one of the things I'm illustrating is a small project. This is one faculty member, one graduate student working together. Text retrieval is amenable to working at that scale and to making contributions. So that's the one we'll talk about. So the way that you get parallel text is you dig it up. This is the Rosetta Stone, which is from Egypt, which is in Africa. Good, got it. And you can see that we don't know what they were writing, but they were writing it in Egyptian, which people still speak, and they were writing it in Greek, and they're writing it in hieroglyphics. And so if you want to know what those hieroglyphics say, they just say the same thing as the Greek, and they say it in the same order. And if they hadn't chopped off that part of the stone, it'd be really easy. But you simply do this pattern matching. Now, this is a little inconvenient to have to dig up a rock and OCR it. And so we just get digital texts that are translations. You can get them from all sorts of places. People translate news. Governments in places that are multilingual will generate their parliamentary proceedings in multiple languages. On the web, you can go crawl to find translations, but that's a little dangerous because what you find is translations from Google, or even worse, from Bing. No, I'm sorry. And that's not what you were looking for, right? What you were looking for was translations from humans. And so you have to build a machine translation detector. And you put an empty system in here. It finds things that looks like translations, finds things that don't look like machine translations, and then goes and grabs it. So that's a way to get parallel text. That approach is called paracrawl. And of course, there are religious books that have been translated into as many languages as you can count. And so parallel text is not hard to find. What do? You just drop it into Giza++ or the Berkeley Aligner. Tools for this are easily available. They take advantage of regularity in the writing order. So there are sometimes reversals in order, but those are systematic. And the so-called IBM models can easily build a translation probability matrix. So this is what I've drawn here. This is the probability of an English term given the Americans originally did this, right? So F meant French, and then later F meant foreign. So I realize that English is a foreign term someplace, but stay with me. The queries are in English in this problem. The documents are in some other language, which we'll call F. We do this vector matrix multiplication, and we get a vector, which is the vector that we would have seen if we had simply had the common decency to write the language or write the document in English in the first place, right? This is the estimated term counts, if this is a term frequency vector. This is the estimated term counts in English for that observable document in the other language. And you get it just by doing vector matrix multiplication. And this matrix doesn't change. You can build it in advance. And the term frequencies don't change. You can build all this in advance, right? And so you can build a cross-language IR system from any two languages for which you have parallel text using this simple trick. And then the question is, how well does it work? Well, all we do is, Charlie showed us this too. This is BM25. Now, Charlie showed us the kiddie version of BM25. This is the full version of BM25. And in the full version of BM25, you can have words repeated in the query. So there's a query term frequency term. Say that 4 times fast. There's an IDF term, which here is written over here. And then this is that nicely shaped expression that Charlie was talking with us about. And so you have to be able to compute the term frequency, which I've just shown you how to do. And you have to be able to compute the document frequency. That's how often the words occur, the query terms occur in the language, right? It's how rare it is, for which you don't need to do any mapping at all. You can map them if you want to, or you can just get them from any English side source, like GigaWord or the New York Times or whatever. And so this isn't hard. And you can get the average document, or here's the document length over the average document length, and that's unaffected by which language you measure it in. So all these statistics are very easy. Charlie taught you how to build a cross-language IR system this morning. He just left out this part. But there's nothing else to it. Got it? Now you could think of lots of other ways of doing it, and then you could compare this to all those other ways, and this works fairly well. So here's a picture. We came up with, we call this probabilistic structured queries, PSQ, that's the blue line. And we came up with some improvements to it where we would take words that were similar in meaning and map them together. Simple version of that, individual meaning matching. The best one, dual aggregated meaning matching. But I got to tell you, the reason we called it that is we looked at this graph. This is the percent of monolingual performance, as measured by mean average precision, one of those other measures Charlie had, that's achieved by the cross-language system. And you can see that as you include more and more and more translations, you can't include them all because there's a lot of noise in the statistical translation stuff, right? But as you include more and more and more of them, the DAMM1 gets better, and eventually it gets up to 101%, which means that this is searching French, and it means if you want to search French, you should use English queries because you'll do better than you do with French queries. And we saw that and we said, damn! And that's how it got the name. Okay? So you could work on this for a while, but I mean, look, we're already better than monolingual queries. Now, if you were uncharitable, you might point out that an easy way to beat monolingual queries is to build a bad monolingual system, and then we could beat it with a reasonable cross-language system. So we could debate whether 100% is the best you could do, but nonetheless, this is better than the 70% people were doing with dictionaries. And we weren't the only people working on this problem. Like many problems, this was simultaneously invented by 3 different people, working in 3 different frameworks. We were doing it with BM25, and other people were doing it with language models. Anyway, this is a story in 3 parts. And part 1 is, you can do work at that scale by yourself, right? I mean, it's not hard. You guys built a IR system this afternoon, right? After you listened to Charlie for 3 hours. I mean, you listened to me for an hour. Think what you could do, right? So the thing that made that possible was somebody built a test collection for Clay French. If they hadn't done that, we couldn't have done that work, right? We depended upon the evaluation infrastructure other people were doing, and no one person was going to build that. So the problem is, if you're going to work on that, you have to work on something other people agree with you is an interesting problem, right? And Nicola's got to talk. Where's Nicola? Has got to talk Wednesday about how to build this that's up against some other talk you don't want to go to, right? So that you can hear about how to build collections. Because without collections, it's hard to do work like that. Now I'm going to talk next about a larger team effort in which we didn't have a collection, and so we tried to build a collection. And so this is an idea from IBM India Research Lab. They called it the Spoken Web. There were many people at the time. This is, oh gosh, 2010 or so. Many people at the time who were looking to build voice forums where you could call up and leave messages and other people could call up and find the messages, and this was an attempt to provide information services for low literacy users. And the clever thing that IBM had was they used cell phones to make the call, and then if you called this number, and this number had a hyperlink, well, the hyperlink would be to another phone number, and they would use call forwarding to forward you to the other number. And then if they would send a little digital packet along to the other number so that you could implement the back button. And so they were sitting here rebuilding the web out of cell phones with voice, right? And what they found was that they could get a good deal of content, and they were subsidizing the airtime. This was done in India. They were subsidizing the airtime so people could participate. And their idea was that farmers would use this to share information about farming, right? I mean, they had very good altruistic motives, people from India working on these problems. And what they found was that farmers did use the system, but they used the system to sing, right? And the technical problem that, I mean, what would you do, right? I mean, you see what happens with the internet, right? People make up the internet because we think like you can send technical papers around, right? And then people look at cat videos on it. Or what was it, bunny videos, right? So people appropriate these things in different ways. But there was some content there to be found, some important content, and they wanted a search engine. But these were human-computer interaction people, and they weren't going to build a search engine. And so they instead built a list of things that had to be developed, one of which was a search engine. Now, the obvious way to work with, so my phone rang, literally, I was in Australia, and Nintendo Rajput there was like, hey, you want to work with us on a search engine? It's like, sounds like a fascinating problem. And so the obvious way to do it is to build a speech recognition system, and here's how you do that. You build a phone detector to get the phonetic structure of the language. These days you can do without that, but this was the common way at the time. And then you have some idea of all the words in the language and what they all sound like, and you map these things onto those things, and then you have some language model of the things people can say, and you filter it through that, and you eventually get really lousy transcriptions, but that wouldn't really bother an IR person because we get really lousy stuff all the time, and we can do pretty well with it. And so this is one way to do it. So the only problem is, anybody want to guess how many languages there are speech recognition systems for? More than 10? More than 100? No. Yeah, it's 30 or so, right? A little less at that time. Essentially, it's everybody who has money, right? Because it takes a lot of engineering to do this. Okay, so that wasn't going to work. But it turned out, Gareth, where's Gareth? Gareth is solving the problem for us. Gareth likes to run shared tasks. Gareth and Nicola really ought to get together. And he runs a task called media eval, which is really cool because they meet in medieval castles. Think about it. Media eval. Media eval, okay? They do. And they let anybody come up with problems, and then they sort of teach them how to run a shared task. And so somebody came up with a problem. You take 3 Indian languages and 11 African languages, a total of 2,000 snippets, and these 2,000 snippets can be in any of those 11, 12, 13, 14 languages. And you build a system that will find a word, given a spoken example, find that word every place it appears. That's not information retrieval, right? That's word spotting. It's actually what the speech people call it, right? But you must have thought of this already. If you had a word spotting system, you could build an information retrieval system, because the way you build information retrieval systems is the first thing you do is tokenize, which is, well, if it had been speech, we would have called it word spotting, right? I mean, we found the words. So they had some way of doing this matching. And speech people have a very bizarre idea of what evaluation is. So here's their evaluation. This is the false alarm probability, which they can't even put on an ordinary scale. It's a Gaussian deviate scale. And this is the miss probability, also Gaussian deviate. And you can just read off a point here. So it says that you have a 50% chance of making a mistake and missing something if you're willing to accept a 1.5% chance of hallucinating it. Now, 1.5% chance of hallucinating it means that you will hallucinate it every 66 words, right? So you might not want to hallucinate it that often. You might want to hallucinate it down here at point 2, in which case you're going to miss 80% of the words. But people say the same words over and over again, and if you miss 80% of them and you get 20% of them, you've got a chance of finding stuff. So the question was, could you build an information retrieval system that would work with this system? And the answer was, of course. I mean, it's just so obvious, right? What wasn't so obvious was whether it would work. That you have to measure, and for that, what do you need? What's that? A collection. So they had a collection, and it was a collection of people talking in English. And it worked really well, of course, because their system was like really well tuned for English, where they had a lot of data. So the question was, great, how does it work in some language where we really care about the problem? So what you'd want is an untranscribed collection of spoken content in some language and some queries in that language. Because of this miss rate, you'd like the query to be fairly long, and then find the relevant spoken content in the collection. And, you know, if Nicola reads this, we'd have a test collection next year. I mean, this is a fairly straightforward process. You just go out and you already have a voice forum, right, with the people from Gujarat, farmers who are singing. And they post questions, they post answers. The agricultural outreach people post announcements. We built 50 queries. We had about 3,000 documents to search. We did top 10 pooling. I mean, this looks exactly like the stuff that Nicola is going to tell you about, except that all the relevance judgments are done with people with headsets on. So it turned out we had a student from Gujarat who had gone to university in Gujarat. So we hired her and asked her to organize the people who were doing the relevance judgments. And it turned out that she had come from some other part of India and didn't speak Gujarati, right? But we were already paying her. So she found people who did speak Gujarati, and we did the relevance judgments. There were 3 of them. And this is a sort of a classic way to figure out if people are doing good relevance judgments. So this is the first half of the experiment. This is the second half of the experiment. The relevance assessors talk in between. This is relevance assessors A, B, and C, A, B, and C. One would be perfect agreement. You can see that B and C get along really well, and you can see that we fired A, right? And B and C built the collection. Okay. Now, here's the trick. It turned out that a fellow I knew at a university 30 minutes away from my office had built one of these systems. And what you did was you simply took all the audio in, and it took every second in the audio, or every actually tenth of a second in the audio, and it just made little windows, and then it slid it across every other tenth of a second in the audio, and it asked, do I hear the same sound? And if I do, I put a dot there, right? Well, that's actually pretty fast. You can build a dot plot pretty fast. Then the problem is, find straight lines in the dot plot, right? So for example, this straight line says that this character, this is a text example, is the same as that character, right? And, well, all these characters are the same as all those characters. That's how we built the example, so we got a main diagonal. But we get this off-diagonal thing because it's text processing versus speech processing, and there's the first processing and there's the second one, right? And then what we do is we see this thing up here and we go, hey, there's this thing up here that's this long, it's on the diagonal, and so I think that's a term. I don't know if it's a part of a word that gets repeated a lot, like ing or id, or if it's a phrase, it's multiple words. You know, if people say, oh, God damn it, right? But it gets repeated a lot. It'll be a really nice index term. So we just dump out all those index terms, and here's what we get. This is time. And this is the number of index terms that are generated at the time. And so here, these were three different ways, sorry for the messy plot, of thresholding the output. But what you can see is, just look at the red one, that there are 49 terms at this time. And there are 20 terms at every time between here and there. And what it does is it says, we should have thought of this, but we didn't, that if the whole big line is there, then the upper right corner of the line is there, and the lower left corner of the line is there, and the middle of the line is there. All those things are straight lines. I mean, we had some limit on how long the lines could be, and they had to be pretty close to a slope of 1, right? And all this is done with image processing to pull it out, but it overgenerates. And so it gives us too many terms, and the IR people don't know what to do with this. And so we generated a whole lot of ideas. We're like, well, we can do a bag of words, right? That's just, put them all in and hope for the best. That's what doesn't work well in cross-language retrieval, is put in all the translations and just hope for the best. That's why we need this technique here. And the one that worked the best for us was we said, look, anytime we see any of the words that are overlapping, we think they're the same thing. We'll just count them as another instance of the same thing. And so we won't count it again unless we see it twice in 2 different areas. And we'll take the longest one and we'll give it a lot more weight. Okay, so we played around with weighting functions. So one of the annoying things about this field is we don't have any theory. Charlie told you essentially the only theory we have, which is if you divide by 1 over c plus x, x over c plus x, you get something that looks like this, right? And he showed you Zipf's law, right? We're really weak on theory, but we're really good on empiricism because we have, wait for it, what do we have, Nicola, that allows us to measure things? Test collections. Okay, so we whipped out our Gujarati test collection, and we can measure how well we're doing. And this is a little hard to read, so we build in the animation. And so you can see the bag of words gets 0.176 in mean reciprocal rank, whatever the hell that means, for the 38 queries that had at least one relevant document. There's no sense measuring things for queries that don't have relevant documents. And it got 0.28 for this LWD thing, which is bigger than 0.176, but nobody really cares if it's bigger because there are only 38 queries and it might be a random effect. But a statistical significance test says it's not a random effect. Well, that was good. Okay, so we learned something. This is better than that. That doesn't tell us this is the best thing we can do. It just tells us that this is the best thing we can think of. And then if you want to try to interpret these numbers, this is a case of precision at 5. Now, you can't count precision at 5 when there's only 2 relevant documents, because your precision can't be above 2 out of 5, right? So we limited it to the case where there are at least 5 relevant documents, and we get 0.189, which is about 1 relevant out of the top 5, right? So this isn't good enough for what we want to do. We want to use this to respond in speech, and our interface paradigm really isn't going to work very well. Here's our interface paradigm. You know how all this works. Charlie told you we can do rapid indexing, we get short queries, and we show the user 10 blue links. But now I'm going to play audio for the user, and I'm getting long queries from the user. So it doesn't look like web search. Now, we're not the first people with this problem. It's quite common that when you first invent something, you make it look like the thing that you had before, right? So here's an early car, got its engine back here, and it looks like a carriage. In fact, it was called a horseless carriage, right? And most people know this story. Here's one you might not know. When Edison built a light bulb, he was having trouble selling light bulbs because nobody had ever seen a light bulb, so he made it look like a candle. Yeah? That made it easier to sell light bulbs, but it created some problems because people would try to light the light bulb, right? So there are some behaviors of the previous system that you really don't want to inherit. So when you bought a light bulb, when you went to a place that had a light bulb, you would often see a sign like this that said, "This has a light bulb. Please don't attempt to light with a match. Simply turn the key." They didn't have switches on the wall because there was no idea of a switch, right? But there was an idea of a key, so they put a key on the wall, and you were supposed to turn the key, and that would cause the light bulb to come on. And then they would, as a marketing pitch, say the use of electricity for lighting is in no way harmful to health, nor does it affect soundness of sleep, which we know now is not true, since light comes out of our cell phones and keeps us awake. Right? But it was just a slight marketing exaggeration. Okay, anyway, you do not want to build, for what we can do here, a horseless carriage, sort of an internet search engine. You want to do the right thing, whatever that is. And so we started thinking, what would look a little bit like a candle but not really be a candle? And we came up with this. So this is one of these Trek topics that Charlie was telling us about. Now, I have to tell you, I had some students who had a little dyslexia, and they could not say Trek topics. They kept saying tech tropics. And when they finally gave their class presentation, they came with a pineapple and hula skirts to talk to us about the tech tropics. But these are really Trek topics. And this is topic number 274, which is about electric automobiles. What are the latest things about electric automobiles? And what you do normally is you take those words at the top where it says topic : take that off and just put electric automobiles in and hope for the best, right? That's a so-called title query. And it looks a lot like a web query. This is from Trek 5. And we came up with an idea. What we did was we were working in India, and we went around IBM India Research Lab, and we handed people this, and we said, would you please talk for 5 minutes about what you're looking for? Right? Read this, figure out what you're looking for, and just babble. And so here's the babble. So a long time back, one of my friends had a Toyota Prius that uses electric and petrol to increase the reduction. This is the query, right? And it would go on for as long as you like. And the goal of the system is, as soon as it finds a relevant document, it should interrupt you and make you shut up, right? No 10 blue links, one massive interruption. Okay, as Charlie was saying, this is why you need academics, right? You can't make money doing this, but you could change the world. So we took these, we had 30 of them. There were 10 people, and every one of them did 3 topics for us. So we had 3 people do the same topic. And these are 3 people who are doing that topic. And the one I showed you is the red one. And this is the reciprocal rank. So when it's 1, there's a relevant document in the first position. And when it's 0, there ain't no relevant document anywhere in sight. Make sense? Okay. And so the green person couldn't find a document to save their life. I mean, there's no stopping question here. They never find anything. The red person, they talk for about 45 words. Things start to get good by about 55 words. We've got a document in first place. They keep talking and eventually knock the document down to second place, right? And so what you'd really like to do is, just as soon as the document gets to first place, you'd like to say, hey, I got an answer, and barge in, right? Well, this is not an information retrieval task. Nobody knows how to solve this. You can't do learning to rank. You do learning to stop. How do you do learning to stop? Same way you do learning to rank, right? You just show it lots of examples, compute lots of features. It's a machine learning problem. And the question is, can I guess when to stop, right? And so we ran ASR because we thought it would be unfair to run on the human transcript that I just showed you. And the system guesses at time 0 that it doesn't have a good answer. And it guesses that because one of the features we give it is, it's time 0, stupid. Don't guess that you have an answer yet, right? So one of the features is, how long have they been trying? And other features are, do we have grammatical words? Do we have an easy reading order, a reading difficulty level? Is this a hard query by a query difficulty measure? I mean, it's just every feature you can think to put in. And anyway, the system, as you saw before, eventually gets better. This is the system doing its thing. And we guess no, 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 right? So these are all true negatives. And then we fail to guess yes when it gets here, until we get to there. So our measure of error is, we guessed yes at 63, and we could have guessed yes at 57, right? And we want that number to be 0, right? So we just measure that, and we sit here and we tune the system so that it does that. And it does that really well on this particular query, which is how it gets in the talk, right? So we have measures that show that, this is an EMNLP paper, that show that we can do this reasonably well on average. Not this well, but reasonably well on average. So we can now have a system that you babble, and, well, this was using English ASR, so we'd have to do something to get it over into the other language, but we could have a reasonable belief that you could barge in. Okay, so this is a larger project, right? We had to build a test collection. We had to have friends that did the speech stuff. It had to be the magic moment. Gareth had to have done his thing with MediaVal. You see how there's sort of a time to solve a problem when the pieces come together? And you can be there to help stitch it together. But this is team science. Got it? Second version? Okay. But it's a story in 3 parts. If there's time before my flight leaves. There is. So cross-language speech retrieval. Now, if you thought that was team science, this is team science. On January 6th of this year, 3 weeks ago, a little less than 3 weeks ago? No, exactly 3 weeks ago, at 9 a.m., actually 8:55, we received an email that said Pashto. And the task was to build a cross-language speech retrieval system in Pashto. Now, how would you do that? Well, you'd build a Pashto ASR system, which, anybody remember back at the beginning of the talk, the basic idea? You hold its nose until it turns blue, and then it looks like text, right? So we just make it into text. Of course, there are errors when we do that. And then, skipping some of the annoying details of Pashto orthography, you translate it into English using an MT system. So you simply have friends that like to build MT systems. They build an MT system. This is the Google solution, except this isn't Google Pashto. This is University of Maryland Pashto. And then you just do ordinary English IR. So essentially you hold its nose until it turns blue twice. You give it the English query and off it goes. You might imagine the people paying for this are not trying to serve Pashto queries, right? They're trying to take English queries and find out what those people who are talking Pashto are talking about, right? Once you have the picture, it's pretty easy to flip it, right? So this is a Robin Hood play. Meanwhile, this is the new work we're doing. There's nothing new about that. The Pashto text comes in here, we give it the English query, and we do that to it. And now I have two guesses of which ones are the ones to find. Except that there are three machine translation systems, one of which does n-best neural machine translation, another one does one-best neural machine translation, another one does statistical machine translation. So I got three machine translation systems, plus this probabilistic structured query thing that I showed you before. And I can do this with and without stemming. So Charlie told you that if you're an academic, do stemming, unless you're Charlie, in which case you'd be careful about it because you know it could be dangerous. But here we can stem the training data. We can stem for the MT on both sides and translate stem to stem. And then if we don't have a whole lot of MT training data, we have a denser training setup and we can do better. So we can do that, but that's less precise. And we can take all of these things. So we generated about 50 of these. You can take all of these things and toss them into system combination, a well-studied problem in monolingual retrieval that somehow the cross-language retrieval people didn't ever look at in a very systematic way. So people have tried specific things, but there's not been any of this make everything you can think of. So we have a version of this that we did for Lithuanian in which we generated 300 systems. And we did a calculation on the back of an envelope of how many systems we could generate, and that number turns out to be about 1,500 systems with, you know, all different kinds of character normalization and different query processing and the like. Anyway, our good friends who are paying for this at IARPA don't want a ranked list. They want a set, and we're IR people, so we only know how to make ranked lists. So we make a ranked list, and then we just chop it off and hand it to them, right? Except you have to figure out how many to chop off, so we have some score cutoff on the normalization. Now I'll skip over all the details of how this works, although I'm happy to send anybody the report on it. But I wanted to show you how well it works. Now there are two things to notice here. One is, this isn't a measure you've seen before. This is maximum query weighted value. But I can tell you that the highest possible value is 1, and 1 is good. And the lowest possible value is minus 40, and minus 40 is bad, right? And I'll show you in a minute more about it. But in any case, that suggests that 0.35 might be reasonable because it's not minus 40 anyhow. Where was it minus 40? In Montreal, centigrade. Okay, Celsius. This is the performance on text, and this is the performance if you don't have that trick, right? So this is the performance using MT, so it eventually gets nearly as good, and this is the performance on speech, right? And you can see the speech is not as good as the text, but the speech is a whole lot above minus 40. And the other thing I want you to notice is, this is January 6th at 8:55 in the morning, and this is 11:55 at night, 4.5 days later, right? So anybody who tells you this is hard just means they're not prepared, because if you have all the pieces, you can build this in less than 5 days. Now, of course, you have to have friends that know about speech recognition and machine translation to do that, and you have to have thought about all the cutoff issues and the character normalization issues and stuff like that. So there's a large team of people that did this. This is done by about 20 people. And the person building the neural machine translation system was in, anybody want to guess? Wuhan. And is still in Wuhan. So this was literally scattered across the globe. We had somebody in Qatar for this as well. I was in St. Martin. I think I got the better end of the deal. This is the evaluation measure. Evaluation measures for sets are a bit of a lost art, but the F measure is what people usually report. They usually report F1, which says I care about recall and precision just as much, but if I care more about recall, I could use F3. And so F3 is a very highly recall balanced measure, so it peaks pretty far over in the recall space. And this is the query weighted value here, and you can see it has a maximum about the same point that F3 has a maximum. And so you could think of maximizing this as maximizing that, right? And so the numbers I've been showing you to a close approximation are F3, they're a recall biased measure, which is what you might want if you were trying to figure out what those people were talking about. This is the data you have to have. You need about as much ASR training data as 10 people working 2 weeks could make, right? So it's 80 hours of data, and 80 hours takes about 10 hours per hour to transcribe well, and so it's about 800 hours, and if you do the math, it's 10 people in 2 weeks. The machine translation takes 40 bilingual people. This can be done by monolingual people, right, in Pashto. 40 bilingual people working for 2 weeks because they have 800,000 words of parallel text, but you don't really have to do this because we have this paracrawl thing that one person can run and go find that level of parallel text, right? So the parallel text problem actually isn't the problem. This exists in nature in many cases, but if you had to build it, that's what it would cost you. And the IR person, you could have just one person build the relevance judgments in those same 2 weeks. So you need 51 people to build this stuff for 2 weeks, and then the 1 week show I showed you can be done. And of course, you could do some interleaving. So that's a measure of the cost of being able to do the translation, which requires words, on top of the speech, right? But you could do that. That's within the bounds of feasibility, particularly because that entire architecture we built, well, open source, anybody can use it, right? It runs in the so-called cloud, which, as you know, is not really a cloud. It's a computer in Iceland. Okay. These are the word error rates in Pashto. By Wednesday, data came Monday. It was about 50%, about 45% by Thursday. One lesson I want you to take away from this is that the IR people are smarter than the speech people, because when the speech measures get better, what happens? Their numbers get smaller. I mean, just try that. Go to somebody who wants to pay you for something and show them something going down and ask them for money, right? If you just plot 1 minus this, you'd get money, right? So all the IR measures, they go up. Don't forget that. Alrighty, you might wonder how well this actually works, and I've shown you a bunch of measures, and so you should believe me, but nobody actually believes me until I show you. So this is a translation of Pashto speech. This translation of Pashto speech was run through a summarizer for English that was already built into the system. I mean, we literally pushed a button and said, okay, fine, summarize it. An hour later, we got summaries for all the queries. So the query here is River Helmond. Is anyone sitting close enough to the screen to tell me if that document is relevant to the comma means and, River and Helmond? You think it is? But over here. Might be? Yeah. So in the ground truth, which was, you know, one person working for 2 weeks, it's relevant. right? So this is somebody who listened to the content and decided it was relevant. Here's another one. So the query is foreign government influence. This is a very popular query in the United States these days, right? Can you tell me if this document is relevant? You don't think so? Anybody?
It's possible the document's relevant, but maybe it's not the
Yeah, right, okay, good. The document's not relevant, and this is the worst summary we generated. I mean, there are some cases where you can tell the document's not relevant. That's a good summary too, right? And this one's hard, right? But you're right, the document's not relevant. And so if you have a really good human, they can pull more out of it than if you have a kind of an average human, right? But the system could do better than it did here, right? This is a limitation. So the IR system, which doesn't just see one word, it sees all those possible translations, it found this document and called it relevant when it shouldn't have, right? And then the human can't tell. So it's not perfect, but did you notice that you can actually tell what they're talking about in some cases? 4.5 days from the phone ringing. The technology exists. All you have to do is make friends with people who work on speech. Anybody here work on speech? Not in this room. Anybody in this continent work on speech? Yeah? Okay, make friends. Anybody here work on translation in this continent? Yeah? I'm hoping so, right? I mean, we got 1.2 billion people. Okay, so make friends. It's a team sport, right? These are the things I want you to remember. New technologies allow us to reach new users, but only if you think of it. Nothing here happened because of the technology. The technology made it possible. Somebody had to think of it. And once you think of it, it's actually not hard, right? Charlie showed us how to do it. Crossing language barriers is increasingly easy because the MT systems are so well developed. One of the things that made Pashto work so well is that they handle out-of-vocabulary translation by doing byte pair encoding, and so they land up taking pieces of things when they can't translate entire words, and they'll never go out of vocabulary. They'll sometimes translate like nonsense, but they never generate nothing. They never generate the source language, which in Pashto is not too helpful because it's not written in the same character set as English. Speech recognition is becoming increasingly affordable because we can do it with less training data. We have systems that are designed for less training data. And because we can find training data in nature. Because people put out transcripts of radio shows. And we're like, oh, well, looks like training data to me, right? And so when we're given more than a week, we go crawl the web and find lots of training data, and that's what we're in the middle of doing for Pashto. These technologies play really well together.